So we're going to integrate 1 over a plus sine theta. Note it's important that we have a greater than 1, otherwise we could get this going to infinity at some point. So we're going to use the technique of changing variable. So z equals e to the I theta, which will end up then integrating around the unit circle. So if we make that change of variable, as we dz is equal to z times I d theta, and sine theta is equal to 1 over 2I z minus 1 over z. So if we substitute those results in, we can just write straight away that this is equal to the integral around the unit circle of d theta is 1 over I z, so we can take out a 1 over I, and dz, and we've got z from the d theta equals dz over 1 over iz, and let's just multiply through. So we've got az and plus 1 over 2iz squared minus 1 over 2I. Okay, so let's try and make things look a bit nicer by multiplying top and bottom of this expression by 2I. Okay, so that will then cancel out this I, and we'll have 2 times so z squared plus 2iaz minus 1. Now, we are going to have to work out where the poles of this are. The whole idea is that, okay, all we need to do now is evaluate this contour integral. And to do that is 2 pi I times the sum of the residues of the poles which are inside the unit circle. But we need to know where are the poles of this function. So let's make life easy from the point of view of writing, and just rewrite this as z minus z plus and z minus z minus. Okay, the reason for doing that, obviously it's a quadratic equation. I'll get minus b plus or minus b squared minus 4ac over 2a as the roots of this quadratic equation. But I'll write those roots for the time being as z plus and z minus. The reason for this will become clear. I can now just go ahead and work out what these things are. So z plus or minus is equal to, just using ordinary quadratic formula, I've got minus b plus or minus b squared, which is minus 4a squared minus 4a, so that gives me minus minus gives me divided by 2. So that is I'll take out a factor of I and then write it as the root thing first. So it's plus or minus I'm taking out a factor of I, so I'm doing minus. I'm taking out that factor of minus. That leaves me with a squared minus 1. The reason for doing that, obviously, is that a is greater than 1, so I want to keep things as not too confusing. Okay, so yeah, a squared is greater than 1, so this is definitely going to be negative inside the square root. So I'm going to have an I anyway. That goes well with this. So then I'm dividing by 2, and I just get that left over. Okay, so that's my z plus and minus, fairly straightforward. Now the essential thing is that we need to work out which of these, z plus and z minus, is inside the unit circle. Okay, so let's have a think about this. Obviously, the z minus is going to be outside, because remember a is greater than 1, and if we choose the minus roots, this is going to be minus and a minus thing. So the z minus is going to be out here somewhere. That's going to be the z minus outside. We could then maybe argue that since we know the answer to this can't possibly be 0, the other one has got to be inside. I think that's probably a reasonable way of arguing it. But if you want to be extra thorough and prove that the modulus of z plus and z minus is, the modulus of z plus is definitely less than 1, then we can do it quite easily. And there's a trick involving polynomials that you ought to know. If I expand this, then what happens? I get z squared minus z plus z minus plus z minus plus z minus times z plus z plus times z minus. So then I can compare, this thing here must equal this thing here. And that tells me that minus 1 must be equal to z plus times z minus. So therefore, the z plus modulus times z minus modulus must equal 1. We already know that z minus, the modulus of z minus is greater than 1, therefore the modulus of z plus must be less than 1. So we know for certain that z plus is inside. So all that remains to do is to work out the residue. So we need the residue of this. In this particular case, it's probably, I'm just looking at the method. So we need the residue of this at z plus. In this particular case, it probably is actually easier to use the direct method. Anyway, so is it? Just because if you differentiate this, you'll get 2z plus 2ia. Well, okay, it seems, anyway, you can use either method. So we're evaluating at z plus, so that means we multiply by z minus z plus, we get rid of this, and that just leaves us with sorry, I've got a factor of 2 here. That just leaves us with 2 over z plus minus z minus. And that is equal, if we subtract, if we get z plus minus z minus, then these cancel, and we end up with 2 lots of these. So we get 4i root a squared minus 1 sorry, that was wrong. This goes on the bottom, so we have 2 lots of a squared minus 1. So the final answer is, I've lost an I somewhere. Oh yes, I got an I from there, so there's an I at the bottom there. So final answer is 2 pi I times the residue. So I is equal to 2 pi I divided by I over root a squared minus 1, and we get that's equal to 2 pi divided by root a squared minus 1. That's our final answer.